I'm going to go through introduction, motivation, problem statement, and methodology, literature review, data model, proposed result, contribution, conclusion, and references. Now, the problem overview is, artificial neural network, we use application in many popular areas. An activation function that we use is tangent hyperbolic function, which is shown in figure 1, and is e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. This function has nonlinear element, and also division makes its implementation on hardware a little bit tedious. Our motivation is, to come up with a hardware implementation of an accurate tangent hyperbolic function for implementation on a digital neural network method. Our problem statement is, why tangent hyperbolic function is, first of all, is easily differentiable. It's compatible with the derivative-based learning approach. Be able, to use various techniques. Basically, paper is approximation of. We have coordinate rotational digital computer, which is the CORDIC approximation method that we use. But apart from that, we have other techniques like using the lookup table, range addressable lookup table. We can use piecewise linear application, and there are many more. In this paper, we use only 2 approximation methods, CORDIC and power of 2. Now, the methodology that we have used is the input that we have is a fixed point arithmetic, 14 bits of word length, 4 bits for integer, and the rest for what we call, the non-integer part. And we are going to show you that how we do the approximation with these techniques that we have. The implementation platform that we have, the input is from -4 to 4, and 14 bits of word length, as I said, that 4-bit integer, and fractional with 10 bits. We use the MATLAB 2020A as our software and HDL coder toolbox of the MATLAB that we've used. And we use the FPGA Xilinx 13.4 Vivado 2019 version and model sim that we have used for this platform. Now, the artificial neural network we have consists of input that go through a bunch of weight of W1, W2, W3, and they add up, and it goes to the activation function, which is either approximated with power of 2 or CORDIC, and the output comes out. And that's basically the model that we have adopted. The model step, the fixed point input goes to the approximation of tangent hyperbolic function, and implementation comes on a FPGA that we have explained. Now, in order to translate MATLAB design to hardware, first of all, modeling algorithm in MATLAB, generating HDL code, it is automatically created a HDL code for FPGA prototyping. We verify HDL code, reuse MATLAB test bench to verify the generated HDL code. We create to verify FPGA prototype, implement and verify the design on FPGA. Now, here, is exactly what we've explained. Is here we start with a MATLAB code, and we come up with the word lengths that we set up. We have the approximation function, and we have the upper and lower bound error that we select, and the fixed point conversion, RMS and MSE error, approximate simulation using Simulink, HDL coder, HDL generation, FPGA, and then resource and delay. The approximation, as I said, is two different types that we use, is the power of 2 and CORDIC. And the accuracy measure we have is absolute error, equation 1, MSE equation 2, and RMSE equation 3. These are the errors that we have used in order to determine the quality of the approximation that we have. For the exponential function, if I look at that, e over x is equals to 2 to the power 1.44x. Now, we can basically come up, with a power of 2 approximation of 1.44, which is shown in this basically equation. And as you can see that, practically what we have is bunch of delay and addition or subtraction we perform. And this is, how we can get a power e to the power of x approximated by the power of 2. Now, here, is practically showing the different level of approximation. This is, instead of having 1.44, this is, I have 1.5, and this is a little bit more what we call, or better approximation of the 1.44 that we have, in this method. Now, if I look at it, this is the curve which is showing that if we approximate e to the power 1.44 by to the power minus 1.5x, this is basically the curve shows the approximated and actual. And this is, practically shows, how we will be able to get, a good approximation even with one bit. Now, if I go through different, what I call, a set of approximation that we have, 1 to the power 1.5x versus to the power 2 plus 1 minus 1.4 minus 1.8. One of the things is, if I use different word lengths, you could see that, the errors for each is shown here. Now, if I look at here, the minute, we have extra terms for approximation, the error goes way down and approximation is going to be much, much better. Of course, if the word length is lower, we're going to have more error as it shows in this table. Again, here, shows the delay that this approximation is doing. Definitely, if I have to the power 1.2x, you're going to have less delay rather than going to the point 1.4375x, which has, more term. You're going to have, extra delay as a result of the addition and subtraction you perform. And the power consumption is more or less, is the same. And the maximum frequency that we have used from 102 megahertz goes to 1.1 megahertz. And here it shows that, the resources we used in terms of the lookup table, then in terms of the RAM, in terms of the flip-flop, and input, output, and everything, it shows that, how basically these power of 2 approximation are using. Now, the CORDIC algorithm is a very efficient algorithm for approximation of the tangent function, sine, cosine, and e to the power x type. Is one thing that is iterative and has a very, very accurate, basically, results, Here, we are looking at the CORDIC approximation of the tangent function for the word length of 10 and fraction of 10. You could see that, the error that we have is practically, 0.5 10 to the power minus 4, which is quite good, And here again, it goes through the various type of CORDIC approximation for a 16, 14, and 8 word length. You could see that, the RMSE error and also MSE error is quite acceptable. In fact, it's quite good. Now, when we look at the CORDIC approximation result, again, in terms of the resources that they use, in terms of the LUT RAM, and the percentage of the flip-flop and I/O devices, you see that, what we have in terms of the MSE and basically RMSE, and also in terms of the delay that they generate is there. In fact, the delay is more than what we have for the power of 2 approximation, but the accuracy is quite good. Now here, we have the what we call it, the performance of the power of 2 with a CORDIC in terms of the resources they use, and in terms of the what we call the RFME error. You see that, definitely the CORDIC has a much more accurate response than the other two. And here, again, it goes through the 2 approximation method in terms of the frequencies that we use. You see that for CORDIC, we're going to have less clock frequency that we have, for the power of 2 approximation. In conclusion, we have presented 2 approximation method for implementation or hardware implementation of tangent hyperbolic activation function. Our study shows that the power of 2 approximation is most hardware efficient technique, while CORDIC method gives best delay result for accuracy of the 2 approximation method. CORDIC algorithm shows superiority to power of 2 approximation method. And that's basically conclude my talk, and I'm ready for any question that you have.